You've probably heard that Earth has an invisible shield, its magnetic field. But what happens when that shield gets a dent? Well, today, we're going to dive into a totally new way of understanding a really dangerous and growing weak spot in that shield, something called the South Atlantic Anomaly.
And this quote right here, this is the core idea that could change everything. See, this new way of thinking says we shouldn't just be measuring a weak spot on a map. We should think of it as a dent in a bubble, a dynamic, three-dimensional thing. It's the changing shape of that dent that might actually tell us a much, much deeper story.
Right, so before we get to the dent, we gotta understand the bubble itself. So, what exactly is this invisible shield? Well, Earth's magnetosphere is basically this huge cavity carved out by our planet's magnetic field. It's constantly pushing back against a stream of particles from the sun, the solar wind. And you can see here, the magnetosphere isn't just some simple shield. It's actively deflecting all this harmful radiation, and it traps charged particles in these structures really far from the surface, like the Van Allen radiation belts. It's this incredibly dynamic protective bubble, and we're all just living safely down here inside of it. Okay, so that's the good news. But that brings us to the problem. Over this huge patch of the globe, that protective bubble is actually being pushed inward. This is the South Atlantic Anomaly, and believe me, it's a growing worry for scientists and engineers. So here's what's going on. The SAA is the spot where our magnetic field is at its absolute weakest. Imagine our magnetosphere is like an inflated balloon. Well, the SAA is kind of like a finger pressing into it, thinning out that protective layer. And that lets nasty radiation from the inner radiation belt dip way, way closer to Earth's surface than it should. And the scary part? It's not standing still. This thing is on the move, drifting westward. And even more than that, it looks like it's developing a really complex internal structure. It might even be splitting into two separate weak spots. Now, this is a huge deal for all the technology we rely on. Any satellite flying through this region gets blasted with radiation, which can cause data glitches, computer crashes, and even permanent damage. And this is where the new thinking comes in. What if tracking the SAA's location and its strength? What if that's just not enough? Maybe we've been asking the wrong questions all along. The real key might not be how strong it is, but its shape. And this slide, wow, it just lays out the shift in perspective perfectly. The old question was static, right? How strong is the field at this one point, right now? But the new question is so much more dynamic. How is this whole system behaving over time? What kind of recurring patterns or loops does it trace as it changes and evolves? So, by treating the SAA as this dynamic object, we can analyze its fundamental shape, or what scientists call its topology. It's kind of like how a donut and a coffee mug have the same basic shape because they both have one hole. By focusing on the essential shape of this magnetic dent, we might be able to predict how it's going to evolve, and maybe even see the signs that it's about to split. Okay, so how in the world do you actually do this? I mean, to analyze the shape of a dent in a magnetic field as it changes over time, you can't just use a ruler. You need a completely new set of tools for thinking about it. And here they are. This new framework gives us three kind of mind-bending ways to describe what the anomaly's doing. We can count its recurring patterns, or loops. We can measure its rotational change, or twist. And we can check how much local information is needed to understand it, its locality. Let's dig into that first one. Counting loops. This is a really cool way to put a number on the recurring patterns in the data. Think of it like this. A simple, stable dent might show a simple, predictable pattern, just one loop of behavior. But what about a more complex, unstable phase, like right before the anomaly splits? Well, that might show a whole lot more tangled loops, signaling that a major structural change is about to happen. And this isn't just some abstract theory. The source material actually makes a prediction we can test. It suggests that before the SAAs started splitting, its loop complexity, that's this beta value here, was pretty low, around 0.3. But during the split, that value is predicted to jump way up. Now, if the data actually matches this, it would be solid evidence that the SAA's evolution involves a genuine rewiring of its structure. Pretty cool, right? Now, the second tool, measuring twist, is looking for something else. It asks a different question. Is the weak spot just kind of drifting across the globe, or is the magnetic field inside it actually rotating? If there's a real twist, that would suggest a much deeper, more complex change is happening, maybe even linked to the flow of liquid metal way down in Earth's outer core. So, okay, counting loops and measuring twists. This is all fascinating science. But what does it actually mean in the real world? Why should this matter for us on the ground and for all of our technology up there in orbit?
Well, it turns out this new viewpoint has some really direct practical applications. For one, it could lead to way smarter hazard maps, helping satellite operators plot safer orbits that just avoid the most dangerous parts of the SSCA altogether. It could also help us design better onboard systems for satellites so they can detect hazards more efficiently. And maybe, just maybe, it could give us early warnings of major changes to our planet's magnetic shield. And that idea of smarter detection is no joke. For instance, during a really complex phase, like when the SAA is splitting, a single satellite might need to analyze data from hundreds of kilometers of its own path just to figure out the hazard it's flying through at that exact moment. Understanding this scale or its locality is absolutely crucial to designing better protective systems.
And this all brings us to one last really forward-looking question. The South Atlantic anomaly is our planet's own natural laboratory for a deformed magnetic bubble. So if we can truly master the physics of this inverted bubble, what could that teach us about one day building our own artificial magnetic shields, maybe to protect spacecraft and future astronauts on their long journeys into deep space?